Today we will be covering correlation, and we will be covering how to actually do this on Stata, and this will correspond to your first Stata lab. Up until now, we've been talking basically about descriptive statistics. So we've been talking about mean, median, and mode, percentages, just ways to collect, organize, summarize, and present data. What we'll start moving into is inferential statistics. So with this, we'll actually make inferences, we'll test hypotheses, and we'll look at determining relationships between variables, as well as eventually making predictions. From here on out, when we start running statistical tests, this is going to be useful for you. You should ask yourself, am I looking for a relationship between variables, or am I looking for differences between variables? Whatever you want to figure out is going to drive your hypothesis, which will then also inform the statistical test that you will run to answer that hypothesis. And the next few lectures will cover tests to determine the relationships between variables. And correlation is going to be one of the more basic ones. So correlations are used to quantify the degree of relationship or association between two variables. When we calculate a correlation, we get a number which indicates the extent to which two variables are related or associated. And that number is called Pearson's product moment correlation coefficient. We can just say Pearson's coefficient. We're basically just looking at coefficients. And Pearson's coefficient is the number that we get when we run a test. And it also represents the correlation. This will make more sense in a second. This is an example of a research hypothesis where we might use a correlation as a statistical test. So let's say that we wanted to understand the relationship between smoking and cardiovascular disease. A refresher, the null hypothesis would be there is no relationship between smoking and cardiovascular disease. And the alternate hypothesis, which you would see more in research, is that there is a relationship between smoking and cardiovascular disease. Another example might be there is no relationship between upper body strength and lower body strength, and there is a relationship between upper body strength and lower body strength. So those would be two different research questions. Now take a second. If we were going to look at this research question, what would be the independent variable and what would be the dependent variable? So in this case, we would think of cardiovascular disease as most likely being the dependent variable in this, because logically, having cardiovascular disease would not cause somebody to smoke. More than likely, it's the other way around. What about in this case? Is there a relationship between upper body strength and lower body strength? Now, is there actually an independent variable and a dependent variable with this research question? Not necessarily, and when you do correlation, it's a little bit tricky to tell if something is an independent variable or a dependent variable, and you have to really look at the research question. So in the example of upper body strength and lower body strength, we can't really say that there's an independent or dependent variable. We would just be looking at relationships. So we can't say that one causes the other. And as a matter of fact, you can actually never make this claim with a correlation. With correlations, we are just looking at relationships. We're not able to determine causation here. So again, this is important, but correlation does not equal causation. That's a pretty common saying in statistics. So we're not claiming that one causes the other. Cause and effect may be present. For example, if there was enough research that looked at incidences of cardiovascular disease and smoking, and that might help us infer that there is a relationship. But again, correlation is not causation. What does correlation give us? Correlation gives us 3 pieces of information about the relationship between variables. It gives us the strength of the relationship, the direction of the relationship, and then also the shape of the relationship. So just a refresher, Pearson's correlation, which will be symbolized as R, you'll see this when we actually run statistics, is what you'll get. It's the answer you get after conducting the correlation. When we do this kind of correlation, we would only be doing it with ratio or interval data. Sometimes ordinal data is used, but for the most part, we want to stick with ratio or interval data. Now, when you get a correlation, if we're looking at the strength of a correlation is always going to be from -1 to 1.0. Those are the only ranges that correlations can come in. A +1 relationship would indicate a perfect relationship. A 0 would indicate no relationship, and then a -1 would indicate a perfect inverse relationship. This is the equation that we use to get correlation, but honestly, you don't have to worry about that because we're going to be using a computer software to get this. So I talked about only wanting to use ratio or interval level data when you're running a correlation. So take a second and think about which one makes more sense to do a Pearson's correlation on. A research question where we're looking at the relationship between an individual's sex, so male or female, and number of push-ups. And what if we were looking at number of push-ups and then a bench press max? Which one would make more sense to run a correlation on? So in this case, sex is not racial or interval level data, it's nominal. So this Pearson's correlation would not be a good test for this kind of research question. But because these are all interval level data, maximum number of push-ups a person can do, and then also their bench press max, then that would be an appropriate test if we're looking for a relationship between those two measures of upper body strength. So when we look at a correlation, we'll look at strength. So how closely are the variables related? Is the strength of the relationship weak or is it strong? So if you get an R value that's 0 to 0.9, that would generally indicate a variable. If it's 0, there's definitely no relationship. Up to 0.9, those are very low strength relationships. As the numbers go up, and notice it doesn't matter if it's plus or minus, just as the numbers go up, the strength of the correlation improves. So 0.60 to 0.79 would be moderately high. 0.8 and up would be a very high correlation. So that was strength. Now direction. So direction refers to just positive or negative. So positive correlations, high values of one variable are associated with high values of the other. So for example, GPA and SAT scores. Usually if someone's GPA is high, their SAT scores are high. Physical activity levels and also physical fitness levels, or in fitness levels. So if somebody's more active, generally their fitness levels are higher. With negative correlations, high values on one variable are associated with low values on the other. So for example, depression and exercise. The more people exercise, the less depressed they are. So that's inverse relationship. BMI and fitness level too. Generally, if people are more fit, their BMIs are lower as well. And then there's no correlation where neither positive or negative, so no relationship exists between the two variables. Then we might also want to look at shape. So we would get a visual description of a correlation, maybe presented as a scatter plot. I'll show you some pictures of that, in which scores for each subject on two variables are plotted with one variable on the x-axis and one variable on the y-axis. So here would be some examples of shape. What does the relationship look like? And what we'll be dealing with for the purpose of this class is just linear relationships. There's examples of curvilinear relationships that might look like this, but we're just going to be dealing with linear relationships. So if we see on this x and y axis, as whatever value for x goes up, the value for y also goes up. And it's a pretty straight line. So that's a high positive correlation between x and y. Now, if we look at this information right here, it's a little bit more spread out, but still as x goes up, y also goes up. So that would be a less strong but still positive relationship between X and Y. In this example, things are all over the place, so there's no correlation. This would be, again, as X goes up, Y goes down, so it's a negative correlation, and notice that the data is a little bit more dispersed, so the strength is going to be less than right here, where the data is more clustered, it's a nice straight line, and again, it's negative because as X goes up, Y goes down. So you also might want to evaluate the size of the correlation coefficient, and this will, again, it will make sense as I actually show you the information on Stata. But you'll get your Pearson's R, and that will be a number which would be something like this. Or if we went to strength, so you'll get some numbers such as this. And we could use a Venn diagram in order for this to make sense. So for example, you would expect overlap between bench press max and push-ups. You would expect those two things to be related. They're training the same muscle group. But if we took something like bench press max and GPA, it wouldn't make sense for those two things to be related. In this case, there would be zero correlation. And then in this case, there would be a pretty strong correlation. So if we did use circles such as this, if circles do not overlap, there's no relationship. If they were completely overlapped, they would have a perfect relationship and the correlation would be 1.0. If the circles overlap somewhat, the area of the overlap represents the amount of variance in the dependent variable or predicted variable that can be explained by the independent or predictor variable. So if I went to this, I might say that a large variance in the number of push-ups performed can be explained by someone's bench press max. So this overlap is called the common variance, and it's equal to that R value squared, so it's R squared. So for example, if two variables, let's say push-ups and bench press, were correlated by 0.8, then they have 64% common variance. So that's 0.8 times 0.8. We just square this number, and that's what we get. So this means that 64% of the variability in the Y variable can be explained or shared with the variance in X. So in this case, we might say that the number of push-ups somebody can do explains 64% of the variance in bench press 1 rep max, or even the other way around, that a person's bench press max explains 64% of the variance in the number of push-ups they can do. And then in this case, we don't know what's causing the other 36% of the variance. And that R squared, so right here, is called the coefficient of determination. So let's go into some Stata examples, and I put this data set up. So what we'll do for our research question, we'll say, are days of aerobic training related to systolic blood pressure? Our null hypothesis is there is no relationship between days of aerobic training and systolic blood pressure. And our alternative hypothesis would be that there is a relationship between days of aerobic training and systolic blood pressure. So let's go to the data. So right here we have days of aerobic training, days of resistance training, systolic blood pressure, BMI, and then waist. So if we wanted to look at that relationship, we would do our command pw core, and then we would do days aerobic, and then we'd want systolic blood pressure, and we want to know if it's significant. So in this case, here is our output. So what we want to know is the strength of the relationship, the direction of the relationship, and then I'll show you how to make a scatter plot out of this as well. So if we want to get a scatter plot, what we can do is go back to this. We go to graphics, two-way graph, and we want to go create, and we want to know what we want our x variable to be, and we want to know what we want our y variable to be. So let's go with days of aerobic training, and let's go with systolic blood pressure. We'll hit accept and then OK. And then that should pop up in a second. So here's our scatter plot. So I'll close that out. So in this case, what's the strength of the relationship? We look at this number, and it's 0.64, so it's a moderately high correlation. And it's negative, which makes sense. You would expect someone's blood pressure to go down if they were more aerobically active. And then the shape of the relationship is linear. So what would we do? Would we reject or accept our null hypothesis? So our null hypothesis was there's no relationship between days of aerobic training and systolic blood pressure. So we would want to reject that null hypothesis because we looked at that and there was a relationship. Now let's try the same exact thing with days of resistance training. So what we do is go back to Stata. We go PW core, and then we're gonna do swap out aerobic training for resistance training. Days resistance, systolic blood pressure, and then we would go sig. So in this case, we could see that the relationship is negative, it is significant, and it's a strong relationship. So in this case, just for this data, the correlation between systolic blood pressure is actually stronger for resistance training than it was for aerobic training. And we could do a scatter plot as well. I just click this again and I will just swap out days aerobic for days of resistance. And we'd get a scatter plot again for that. So what you can do is we can take these as basically being our independent variables, and then these three as being our potential dependent variables. So you've already done days of aerobic with systolic blood pressure. You've done days of resistance with systolic blood pressure. You could run correlations between aerobic training and BMI, aerobic training and waist length, resistance training and BMI, and then resistance training on waist length. So pull up that data set and get some more practice in for using correlations.